A Bose-Einstein condensate, or BEC, is a state of matter that occurs under very extreme circumstances. In this short presentation, I will focus on explaining what BECs are and go through the theory behind them, and I'll just briefly touch on how they can be created in labs and a few of their applications. So to understand the mechanism behind BECs, we recall the fact that bosons are not confined by the Pauli exclusion principle because of their integer spins. At very low temperatures and low densities, a large number of bosons can occupy the lowest quantum state of a system, and the microscopic individual wave functions interfere, becoming apparent macroscopically. One can approximately imagine this phenomenon by considering the de Broglie wavelength of each particle, which increases as the temperature drops. When the de Broglie wavelength exceeds the mean distance between particles, they start to overlap and their individual identities are lost. We introduced the concept of a grand canonical ensemble to realistically model BECs. A grand canonical ensemble is in contact with both a heat reservoir and a particle reservoir, meaning that temperature and chemical potential are kept constant, while both the energy and the number of particles of the system can change. The chemical potential measures how free energy changes with the number of particles, which is obviously a relevant quantity now that we have a changing number of particles. Equations 1 to 3 in my poster describe the mean number of particles in each state and the critical temperature for BECs to form. In figure 1, we see graphs showing the proportion of particles in ground state as a function of temperature calculated using Bose-Einstein statistics. These curves look far different than predictions using Maxwell-Boltzmann's statistics, where the graph only sharply increases when the temperature approaches absolute zero. Now, onto the experimental procedure. The critical temperature for BECs to form is generally extremely low, for instance, 170 nanokelvins for rubidium-87. Two techniques can be used to cool molecules down to such scales: laser cooling and magnetic evaporative cooling. In very broad terms, laser cooling reduces the momentum of atoms by targeting them with photons, and magnetic evaporative cooling allows the evaporation of energetic atoms so that the remaining atoms are cooler. Finally, why care about BECs at all? Well, certain properties of BECs make them very useful candidates for studying certain fundamental physics phenomena, such as blackbody radiation and dark matter. The number of Nobel Prizes that have been awarded for BEC-related research is very telling of their important applications.